But the problem is that there hasn't really been a good way of measuring 2D gel data quality. The technology has been around for, what is it, like more than 2 decades or something. But so far, there hasn't been a reliable way of assuring that the data that you can extract from the images is correct and complete. So you know the saying that, I mean, what you cannot measure, you can't improve. So the question becomes, how can we measure 2D gel data quality, the correctness of the data that you extract using image analysis? So there is an approach that has been used in recent years with reproducibility. So you're trying to look at the reproducibility of the data that you extract from images and use that as a descriptor of its quality. So the thinking is that the more reproducible the data is, the better it is. So reproducibility is generally measured by calculating the mean CV, which is the mean coefficient of variation. And the thinking is that a low mean coefficient of variation is often interpreted as reproducible data. But so the question becomes, can mean CV be used as a metric for data quality in 2D gels? And to answer that, I just want to remind you about the distinction that we made between images, data, and results. So what we're doing here is that we are calculating the mean CV on the data to try to assess the correctness of the data that is building up the mean CV. So to me, that's a little bit suspect, but okay, let's work with that assumption. But consider that CV is defined as standard deviation divided by the mean. And what do you do if the measurements are wrong? The measurements that you use to calculate the value that you're using to assess the measurements. It's kind of a circle argument. And the interesting thing is that if correctness is represented by reproducibility, and reproducibility is represented by low CV values, then you would assume that if you have more errors, that will result in higher CV values. So let's test if this is the case. What happens if you add a constant value to all the measurements? For example, that all the spot volumes get like, just a random factor increase, like the factor 1,000 to all the spots. What would happen to the reproducibility and the mean CV values? What would happen if you don't do any background subtraction? What would happen to reproducibility, and what would happen to our assessment of the quality of the data? Or what would happen if we have a lot of amalgamation of spots, which is usually the case, especially if you have a software that's utilizing the 4th generation workflow with warping images and doing spot detection and fusion image. In all these cases, we can see, of course, that the data would be worse because we are consciously creating problems in the data. And in all these cases also, the average value, the mean value, would go up. If we're adding a constant value to all our measurements, if we have more amalgamation, then the spots would be bigger, and that will drive up the mean. If we wouldn't do background subtraction, the mean would also go up. And if you look at the formula, that means that the CV values would go down. And what we thought before was that lower CV values means high reproducibility. So we would get lower CV values, we would interpret it as higher reproducibility, although we actually have worse data quality. So the conclusion is that you cannot use CV values to assess correctness. And reproducibility is only useful to talk about reproducibility once you have determined that you have correctness. Because, of course, common sense tells you that also errors are reproducible. So all this kind of little excursion here and theoretical reasoning is highlighting the need to assess the correctness of the measurements themselves before you start talking about mean CV values and before you start talking about reproducibility. You need to be able to assess the measurements, meaning the spot detection and matching and the quantities that come from image analysis before you start talking about reproducibility and measuring mean CVs. And then we're back to the main question, how do we do that? So looking at the 2D gel technology, the good news is that with this type of old-fashioned technology, you can look at all the measurements with your eyes because you can see the spots in front of you in the image. You can see the spot outline. You can see if the same spot seems to be matched in 2 different gels. And you can see if the spot outline is encompassing the spot or if it's cutting it in half. That is a strength of this technology, actually. But the weakness or the bad news is, of course, that there are so many measurements. If you have 10 gels with 2,000 spots in each, you easily have 20,000 spots. And it's just practically not possible to go over every single spot and assess its correctness. So what do you do in science when you have too many measurements to assess? What do you do if the population that you're testing is too big? Let's say, for example, that the Swedish government right now would decide that they want to know how many people in Sweden have swine flu. What would they do? Would they call every single Swede to the doctor's office and test them for swine flu? There would be 9 million people in that queue. I wouldn't want to be last in that queue. It would take forever. It would be really expensive. So that is, of course, not what you do. What you do instead is that you take a representative subset of the Swedish population and you test those. And you make that subset big enough so you can draw statistical conclusions from it, and you make it representative enough so you can scale it to the entire population. So you randomize and sample among the population to take a subset, and you test the subset, and you let that test tell you how many Swedes, draw conclusions on how many Swedes would have swine flu. And it's the same thing for the 2D gel data quality control. Let's randomize and sample amongst all these 20,000 spots that I mentioned. Let's say you have 10 gels with 2,000 spots in each. Instead of testing every single spot for if it's correctly detected, matched, and quantified, you can take a subset of these 20,000 spots and you can test those. And what you need when you have selected a subset of spots for testing, you need also visual criteria for evaluating that subset. But you can actually do this since you can see all the measurements with your eyes. So if you're setting up spot detection evaluation criteria, visual criteria for this, something like this. So this would be a correct spot. I think everybody would agree that this is definitely a correct spot. And the spot outline is encompassing this spot and measuring this spot and nothing else. This would give you a correct measurement. And I think people who are familiar with 2D gels will also recognize immediately that this is a false spot. This is not a protein. This is something else that has been creating darkness in the gel. And a third category would be a misshaped spot. And the spot outline is clearly not measuring the full spot body. It's cutting it in half, and actually it's also encompassing something next to the spot. And the fourth category is when the software hasn't detected a spot at all. So this is a missing spot. And using these 4 categories, you can take any spot in any of the gels, and you can put that spot in either of these 4 categories. There is no 5th category, really. It's a correct, it's false, it's misshaped, or it's missing. So here you have very clear visual criteria for how to assess one single spot. You can do the same thing for matching. You can define correct matching as when it's evident that the same spot in 2 gels have been matched. And you can define visual criteria for incorrect matching in the same way. You can see that this is not the corresponding spot. And then we have to define something called correct non-matching, which is when a spot hasn't been matched, but it's correct because there is no spot in that image. And even more complicated, incorrect non-matching, which means that there is no matching, but there should have been one. So using these 4 criteria or 4 categories for matching, you can take any spot pair in any 2 of the gels in your set, and you can put that in either of these 4 categories. So now we have visual criteria for spot detection or visual criteria for matching, and you can use those to classify a randomized subset of spots and match pairs. And that would give you an estimate of the so-called spot and match correctness. And it's quite easy to do. Just as if you would have tested the Swedish population for swine flu, you would say, okay, how many of my subset have tested positively for swine flu, and how many people did I have in my subset? That would give you the ratio, and you would apply that ratio on the entire population. The same thing for spot correctness. You would assess how many spots, out of the spots that I evaluated in my subset of spots, how many were correct according to the visual criteria, divided by how many spots did I test. And that would give you a percentage on spot correctness. And the same thing for spot matching correctness. You evaluate how many match pairs did I deem to be correct versus how many did I test. That gives you correctness. And then finally we define something called combined correctness, which is basically just the product of the 2 factors. So now we have a suggested metric for assessing the correctness of spot detection and matching. We're summarizing this in one parameter called combined correctness. But the key question then becomes, is this a useful indicator of a successful 2D gel image analysis?